Welcome to this instructional video to finish up the notes in Chapter 19. So we ended class on Friday talking about arene diazonium salts. It's a gateway reaction to many different things. One of the main takeaways was that if you have a nitro group on a benzene ring, you can ultimately convert that to many different things on your handout that I gave you. And so an important process of this was reducing the nitro group to an amino group, or going nitrobenzene to aniline. And I gave you three ways to do this that you would likely see. One is Clemenson will work. Number two, iron hydrochloric acid followed by base will work. And then the third way is some type of hydrogenation. And I said that you would want to use hydrogen gas, H2, with platinum, not rainy nickel as we've used in previous hydrogenation. So let's do this a little bit more, and I've written this out just to kind of review it for you. But in terms of hydrogenation used in this making of a diazonium salt, you will not want to use rainy nickel. And one of the reasons is you can also, with rainy nickel, you can do two major things. You can reduce a carbon-carbon double bond, or you can reduce a carbonyl. Well, sometimes in doing the diazonium salts, that would be a problem. Also, rainy nickel is just not good at converting a nitro group to an amino group. So you want to avoid using rainy nickel in making a diazonium salt. In the process of going from nitro to the amino, in the process of making a diazonium salt, you can use, among the three possibilities I've given you, you can use hydrogenation and platinum, because that will do what we want to do. Convert NO2 to NH2. So just an example of the difference between hydrogenation with platinum versus hydrogenation with rainy nickel. If you take our molecule here, which is in alpha beta unsaturated aldehyde, if you use hydrogenation with platinum, you do not reduce the carbonyl. There was no reduction of the carbonyl. There was a reduction of the double bond. If you use rainy nickel and you use two equivalents of it, you would reduce both the double bond and the carbonyl. So let's put this diazonium salt kind of in action. And again, this is going to fall squarely in electrophilic aromatic substitution again, but we have now the diazonium salt as a gateway to many more things that we can put on the ring. So let's do this example synthesis. So what if we start with benzene? I need you to make the molecule on the right. So basically make the molecule on the right starting with benzene and any other reagents that you want. What you know is, well, you've got two things on the ring, and how are you going to put these things on the ring? Well, I think we know that, this looks a lot like Friedel-Crafts acylation could be very useful to us. We've done that before, and so that probably would be a good thing. This fluoro group, though, it's like, wow, how are we going to put a fluorine on the benzene ring? We had no idea how to do that in our previous chapter where we talked about electrophilic aromatic substitution. But now we do have a way to do this through a diazonium salt if you look at the handout that I gave you. So, how are we going to do this? We know that if we can put a nitro group on the ring, we have a series of reactions that will eventually replace the nitro with fluoro. So, what's our strategy? I think the first thing we need to do here, clearly, is to maybe do Friedel-Crafts acylation first, because if we put the nitro group on the ring first, that eliminates the possibility of Friedel-Crafts acylation. You cannot do Friedel-Crafts acylation on a deactivated ring with a nitro group on it anyway. So let's see how this works. So let's go ahead And let's just do our Friedel-Crafts acylation. Pretty standard stuff that we've done before. And again, it doesn't matter where we put this, but I want to put it where it's at on the product, obviously, because that's going to help us out. So, help show it anyway. So now we've done our Friedel-Crafts acylation. The good thing here is the fluoro is meta to the acyl group. So we're going to need to put the nitro group meta to the acyl group. And that is very much in our favor because this carbonyl, this acyl group, is an electron withdrawing group. So if we do nitration, we're going to put a nitro group meta to the acyl group. And that's what we want because we're going to do a straight up replacement of the nitro with a fluoro atom, a fluorine atom. So let's do this. So we're going to just do our nitration next, the standard nitration conditions. So that's what we started with, and now we have NO2. All right, so now we have our nitro group. Our nitro group, think about it like as a marker, as a landmark, whatever you want to call it like that. Because now we can do a standard set of reactions that you'll have to do now to put the fluorine on the ring, or other things on the ring that's in that handout that I gave you. So let's just go ahead and use a reaction we just talked about. We can use hydrogenation with platinum to convert NO2 to NH2. Okay. Now here's a great example of why you would not want to use Raney nickel, because Raney nickel would also reduce the carbonyl. You don't want to mess with that carbonyl because our carbonyl is in the product. Okay. So, what's next? We've got the aniline derivative that we've made. What we know is if you treat this with the NaNO2 with HCl, this makes our diazonium salt. There we go. That's our diazonium salt. Looks nice. And now we are just one step away to our product. And again, I am physically getting out the handout that I gave you in class. And look at that. And we can replace the diazonium salt part with a fluorine if we use HbF4. There we go. That's it. So our strategy was to make the molecule on the top right, starting with benzene. That was our goal. Our strategy was to do Friedel-Crafts acylation first because we needed to get that acyl group on the ring. We know we can put a nitro group on the ring very easily and then convert that to NH2 and then convert that to the diazonium salt and then add a variety of things where the nitro group used to be. In this case, we added fluorine. All right. Well, we want to turn our attention to another class of molecules that can be made from amines but are not amines. They are amides. So I want you to repeat after me, and you can do this 100 times on your own time. Amides are not amines. Amides are not amines. Amides are not amines. They are different. They have different properties. We make amides from amines. And we have a primary, secondary, and tertiary amide, like we've had different types of amines. But we've got to be able to deal with amides. okay, or amides, potato, potato, tomato, tomato. Say it the way you want. I don't care. Just know what it is, okay? So how are we going to make an amide? Well, this shows us here. Typically, we want to start with an amine. And this will work. Again, we can make all three different types of amides this way. In this one, we want to start with an amine. And we want to start with an acid and react it with an acid chloride. And we know that if you want to make an acid chloride, you can start with our old friend, the carboxylic acid, and use SOCl2. We've done that a few times now. And then you need pyridine. And I've kind of come up here and drawn the structure of pyridine to make a big point of why we need pyridine here. We know amines, we know this, we went over this, can have an acid or a base form. Well, the only form that will react in this reaction is the base form, because the base form is going to act as a nucleophile. So you better have that amine in the base form or a reaction will never occur. So what does pyridine do? As I'm showing you up here in the top right, pyridine acts as a base, pulls off the proton of the amine, and then here's the amine, R, and I've drawn it in the acid form here. This is bad. We don't want the acid form. So if you add pyridine as the solvent and a built-in base, you can make sure that the amine that you're dealing with is in the base form and can react. So that's what we need pyridine for. This is a very, here's another example of a nucleophile attacking an electrophile. This carbon of the carbonyl is electrophilic. It has a good partial positive charge. And not to do the mechanism right now, but this will attack here. This will move up. And then eventually the chlorine is going to be a good leaving group. And so what we've just done here is we have made an amide, and it is a secondary amide technically. Wow. When you put a carbonyl next to the nitrogen, that's a much different molecule. That's an amide, not an amine. So what we did was made this bond right here, which we call the amide bond. Okay? So let's do another example down here. We have a primary amine in this case, and we have an acid chloride. And here's pyridine that we need. Again, just to see how this connects up, this is going to react here. This is going to flow up. Eventually the chlorine is going to leave as a leaving group, and we're going to make an amide. So that's what we need to draw here. CH3, CH2, C double bond O. I guess to kind of show where the atoms go, you're going to make HCl in this case as well. This chlorine and one of the hydrogens is really going to be the leaving group. Okay, so we need to take a hydrogen off this nitrogen to draw the product. So we have this. There we go. And then HCl is also produced. Where's the HCl come from? One of the hydrogens from the nitrogen has to go in the mechanism, and the chlorine here has to leave, and they make HCl. And we make, ta-da, this secondary amide. All right. So let's do a few more things with amides. We have some reactions, and I've kind of drawn them out already. You can stop the video and write these down. There's more, but I've kind of trying to narrow the field a little bit. You can go from an amide to an amine. So if you have an existing amide and you need to go back to the amine, you can do a reduction reaction. This is reduction. In the past, when we wanted to go from a C double bond O to a CH2, we used Clemenson. This will not work here with amides. Amides are not compatible with the Clemenson. So we have to use lithium aluminum hydride, kind of a legacy reducing reagent that we've used a lot. So if you want to go from an amide, it doesn't matter, primary, secondary, or tertiary amide to an amine, then you can use lithium aluminum hydride. It's reduction. Don't use Clemenson. Clemenson doesn't work with this particular reaction. What's another reaction? If you start with a primary amine, see, I said it. I'm going to go wash my mouth out with soap 100 times now. If you start with a primary amide, you can use the reagent POCl3. You can make, oh, look at this. We talked about this last time, a nitrile. I would strongly advise you to just go back and collect. Again, you can make these reaction sheets. You don't need me to make these for you. You need to make the reaction sheets. That's how you learn the reactions, is making the sheet, not for me to give you a reaction sheet. It's how many things have we done with a nitrile? Well, a lot. And so a gateway to a nitrile, one gateway to a nitrile is a primary amide. A primary amide. All right, let's continue on just a couple more pages with the amides. This reviews the different structures of amides that we've talked about in the past, or that I've mentioned to you. It's on your sheet. You know, you have your playbook. Remember the playbook? It's got the different types of amides on it. This is just to review them. This is a primary amide, secondary amide, tertiary amide. Again, you know it's an amide because you've got a carbonyl right next to the nitrogen. Well, let's just take a primary amide as an example to make a big point that I want to make. So let's just say we have an R C double bond O NH2. This is a primary amide. What we know, amides can undergo resonance. So let me be a good chemistry citizen, put my lone pairs in here. We can draw a resonance form for amides. This is not available in the amines, by the way, and that's going to be a big deal here shortly. So if you look, hang on. If you look at this, here is a legitimate resonance form for this primary amide that I drew. Make sure we do all the charges correctly. Now, okay, I'm drawing let me just erase this to emphasize. This is not reaction, this is resonance. Is this a legitimate resonance structure? Well, I say yes. One thing we know is that two resonance structures can't have the same net charge. Well, these don't. The one on the right has two formal charges, but they cancel each other out, so both have a net charge of 0. What I'm showing you this for is that this lone pair right here, this electron lone pair, is not available. It is not available. To abstract a H plus, or to react to H plus. So amides are neutral. Amides are neutral. They don't act as an acid or base. They will never have a net charge. That's important for amides. Now, for full disclosure, amides do have a pKb like amines, but it's so high, it's like 14. Then we are just going to say, for our purposes, this lone pair is not really available. And if this lone pair is not really available, then it can't act as an acid or base. So amides are neutral. Amides are neutral. They will never have a net charge on the amide part of the molecule anyway. Okay? Now, so when you talk about ionic interactions with amides, no, that can't happen. Amines, yes. Amides, no. Amides are not amines. Amines are not amides. People mix this up all the time. It's a forecast for pain. I see the carnage. It makes me sad, but I don't know what to do to get your attention on this except make a big deal out of it. By the way, I've just made a big deal out of it. Okay? Now, don't worry. Amides can't do ionic interactions. That's okay, because they are extra special. They're superheroes of hydrogen bonding. So we've said in the previous class, amines form weaker hydrogen bonds. That's a good take-home message here. Amines form weaker hydrogen bonds. I am here today to tell you that amides form stronger hydrogen bonds than normal, if you want to say it that way. So let's put this in the Ricky's red asterisks here. Oh, let's do 2 of them. And we can put it up here too, because that's an important point. So if you look up here, if you look in the middle of the page here at this resonance structure, what this resonance structure is telling you is that these hydrogens have an extra special positive charge, or an extra partial positive charge. Remember, in organic chemistry, these formal charges, they're bookkeeping. They're for bookkeeping purposes. In the middle of the page here, does that nitrogen of the amide really have a +1 charge? Is that nitrogen really positively charged? No. That's just a formal charge to keep up with the net charge. Really, these 2 hydrogens are extra partially positively charged. Let's call them super H-bond donors. Super H-bond donors. And this resonance structure tells you the oxygen is going to be a little bit more partial negatively charged. Okay? When you draw it the way you normally draw an amide, you don't draw it as this resonance structure on the right, you draw it on the left. But I'm telling you, I'm using the resonance structure on the right to make a point. The 2 hydrogens there on the nitrogen have extra partial positive charge. That makes them a super hydrogen bond donor. They form stronger hydrogen bonds. And the oxygen of an amide, of that carbonyl, is extra partial negatively charged. So it is a super the lone pairs on this oxygen, the lone pairs are super hydrogen bond acceptors. So amides are the king of hydrogen bonding. They form very strong hydrogen bonds. Ionic interactions? No, sorry, that's not going to happen. But they are very good at forming hydrogen bonds. All right. Well, the last thing we want to talk about is, I do want to do one mechanism here, is what if you have an existing amide and you want to break it? You want to break an amide bond. And of course, when we want to break a bond, a lot of times we use hydrolysis, which means to break with water. break with water. All right, so let's just take an amide, and it doesn't really matter which type we do. I'm just going to use a secondary amide here, I think. So here's the goal, and I'm going to move this down a little bit. The goal is to break this bond. This is the amide bond. It must be broken, and we must use water to break it. So we have a couple of options here. Typically, to make this happen, we need acid catalyst or base catalyst to make this work. Okay? So what I'm going to do is I'm actually going to move the word amide here. I'm sorry. I'm going to put it here. So let's just use acid catalyst here. Let's just do the acidic version. So what you know, if you have acidic water, you have a lot of hydronium ion. You also know by now that when you have a hydronium ion, or you have acidic conditions in water, and you have a carbonyl oxygen, you're going to protonate that oxygen. So here's the first step of the mechanism. You're going to protonate this oxygen. And again, are all these lone pairs and charges really important? Yeah, they are. Okay? So now, just like previously in this class, when you protonate the carbonyl oxygen, you make the carbonyl carbon a stronger electrophile. This carbon now has a greater partial positive charge, and so we're going to react it with a nucleophile. Well, if you're in water under acidic conditions, what is the strongest nucleophile in water under acidic conditions? It happens to be just water. And if you were thinking hydroxide ion, then I would say no, there's no hydroxide ion here. There's very little hydroxide ion because we're under acidic conditions. So really, water is the strongest nucleophile under acidic conditions in water. That's going to attack the carbonyl. Electrons are going to flow up, and you're going to get this. Again, I'm going to pay extreme attention to lone pairs and charges because that's what mechanisms are about. Curved arrows, lone pairs, and charges. Okay, that's where we're at. So now we've got to do a couple of different things to kind of break this bond. I think the first thing we should do is let's go ahead and take one of the protons off water to get rid of that positive charge. I think that would be the best thing. So we need a base now. Again, right here, water acted as a nucleophile. Well, we need to use water again to act as a base, which is perfectly fine. You just need to know when it's acting as a nucleophile and when it's acting as a base. Well, it's acting as a base when it pulls off a proton. Guess what we are doing? We are pulling off a proton. All right. So, we can come down here. So what do we have left to do? What we have left to do is we still got to break this bond right here. We got to break this bond, and then we got to have one of the oxygens be a carbonyl, and the other one can remain as an OH group. So how are we going to do this? Well, one thing we can do, and I'm going to move this arrow over a little bit. All right. Let's do this. Let's see what we can do. So I'll kind of mark that bond for us, but actually I need this bond to kind of go, this arrow to go away for the mechanism. So how about this? We're going to need an acid and a base to do the next part. So we have water and we have the hydronium ion to be water the base and the hydronium ion the acid. We need this to leave. We need this bond to break, and the only way for this to leave is to make it a good leaving group. And so we need to have some acid around. So here's one way to draw this mechanism that will be just fine. Okay. The proton pulls off this hydrogen. We just established the carbonyl we need. We need a carbonyl because when you break an amide, you're going to get a carboxylic acid and an amine. That's how we made it, right? So what we would be great. Life is awesome if we could break this bond. We could break the bond between the carbon and nitrogen. Well, the problem is that's not a good leaving group unless it picks up a proton on its way out of town. And it just did that with the hydronium ion. So what we get left over is the carboxylic acid plus, look at this, H2NR here. There we go. So when you break an amide, you need to do it in, you can do it in water. You need acidic or basic conditions because you need acid catalyst or a base catalyst. I went over an example of how you could break this amide here using acid catalyst. And so we protonated the carbonyl. We made the carbonyl more electrophilic. We used water as a nucleophile to make an intermediate. We used water as a base during the process. Down here, we used water as a base again. Again, in the same part of the mechanism, we used hydronium ion as a source of acid. So let me just label this for us. This is called acid catalysis because you have the hydronium ion and you don't have the hydroxide ion. That's why you have to have water as the base. So this shows you a legitimate mechanism to carry out the hydrolysis of an amide under acidic conditions. You're going to end up with a carboxylic acid and an amine. So I think that's it for this chapter, and I think we will stop it right there. Thank you.